Hi guys, welcome back to the channel. In this lecture, we are going to calculate the collapse load for this frame structure in which the column is inclined. Okay. So in this frame, as you can see that this column is inclined with respect to the horizontal. In the previous lectures, we have solved problems in which columns are exactly vertical with respect to the horizontal axis. Okay. So now here two points load are acting. One is acting in horizontal direction of magnitude 0.5 W and one is acting in vertical direction of magnitude W. Okay. So basically we need to find the collapse load value of this W. Okay. So first step in finding the collapse load is to find the static indeterminacy of this frame structure. So what is the static indeterminacy of this frame? Okay. And this is the point of natural hinge. Okay. So at this point, the reactions will be one vertical, one horizontal. Okay. At this support, the reactions will be one vertical, one horizontal, and one rotation will be there. Okay. So total number of reactions are 5. Equilibrium equations will be 3. Summation fx0, summation fy0, and summation m0. Okay. So static indeterminacy of this frame is basically 2. Right. And next step is to find what possible location where the plastic hinges can form. Okay, so plastic hinges can form at this B point, under this point load, at this C and D. At A, it is natural hinge, so at this point the moment will be 0, so plastic hinge will not form here. Okay, so total number of possible locations of plastic hinge are basically 4. Okay. So independent mechanism will be will be equals to 4 minus of 2, which is 2. Okay. So in this frame there will be two independent mechanisms. One is beam mechanism. Okay. Second one is sway mechanism. And then we will combine these two mechanisms to get combined mechanism. Okay. So combined mechanism is basically due to beam and sway mechanism. Okay. These are both independent mechanism. Okay. So basically now we are having two independent mechanism. One is beam mechanism, other is sway mechanism, right? So we need to calculate collapse load separately for these mechanisms. Okay. And which one is the load which is will come out to be less, that will be our design load. Okay. So now next step is to calculate what we can say is the the collapse load for beam mechanism, right? So as you can see that in beam mechanism, this is the frame. Okay, the plastic hinge will form at this B point, under this point load, and at this C point. Okay, and it will deflect. The plastic mechanism will look like this. Okay, this deflection is during collapse. Remember that thing. Okay, during. So now at this location, let us suppose this is theta 1, this is theta 2. Okay, this will be theta 1 alternate angles and this will be theta 2, right? This point is B, this is C point, and this is let us suppose E, and this is C. Okay, so plastic hinges are forming basically at B, E and C point, right? And let us show the direction of the plastic movement. Plastic movement will be opposite to this rotation, so it will be anti-clockwise here, clockwise here, here it is again anti-clockwise, and here again it is clockwise. Okay, so this will be the direction of the plastic movement, right? So now if you calculate the collapse load here, first let us find, and this deflection is based, let us suppose this is delta. First, let us find what is the relation between this theta 1 and theta 2. Okay, so delta I can write 4 into theta 1. Okay, similarly delta will be equals to 8 into theta 2. These theta are very, very small. Okay, that's why we can use this relation. Okay, so theta is very small. Okay, so if you equate these two equations, I can write 4 theta 1 equals to 8 into theta 2. Okay, from here I can say that theta 1 by 2 equals to theta 2. Okay, now let us apply the principle of virtual work to find the collapse load for this beam mechanism. Okay, so using the principle of virtual work, if you use the principle of virtual work, it is external work done is equals to internal work done. Okay, actually the total is external work done plus internal work done should be 0, but internal work done will always be positive basically, because work done absorbed is always positive, right? That's why we are saying that external work done equals to internal work done. Okay, so now you can see that we can say that for external work done, what will be the external work done? External work done will be W into this delta. Okay, so this will be W into delta, right? And delta we can replace by 4 into theta 1. Okay, and this is equals to internal virtual work done. Okay, what is the internal virtual work done? Internal virtual work done will take place at the hinges. Okay, will take place at the hinges. So at this hinge location, the internal work done will be MP into theta 1, right? At this location, the work done will be MP into theta 2. In place of theta 2, I can write theta 1 by 2. Okay, plus at this location, I can write MP into theta 1 plus theta 2. Theta 1 is again theta 1 by 2. Okay, right? So if you solve this equation, theta 1 will cancel out. So I can write 4W equals to MP plus MP by 2 plus MP into 3 by 2. Okay, so this will be equals to 4W equals to 3 MP. So from here W equals to 3 by 4 MP. Okay, so corresponding to the beam mechanism, the collapse load W is coming out to be W equals to 3 by 4 MP. Okay, in this beam mechanism there is no role of this 0.5 W. Okay, there is no displacement. We are assuming the beam mechanism, so this 0.5 W won't give any external virtual work done. Okay, so this is the first case in beam mechanism, right? Okay, one more thing I would like to tell here is that direction of theta, okay, direction of the plastic rotation, because we will be need that thing while doing the while calculating the collapse load using combined mechanism. Okay, so let us discuss the direction of plastic rotation. Okay, sign, or you can say that sign of plastic rotation, basically sign of plastic rotation, whether it is positive, negative. Okay, so the direction which we will be assuming, let us suppose this is our beam mechanism. Okay, so plastic hinges were forming at the plastic hinges are forming at these locations. Okay, so here this is the direction of rotation basically. Okay, and direction of movement will be opposite to this rotation. Okay, So this moment, this plastic moment is producing what? Tension outside. Okay, if this is the frame, due to this plastic moment, upper side will be outermost side will be in tension, and bottom side, inner side will be in compression. Okay, this thing should be clear. Okay, when this moment will try to produce tension on upper side, outer side, and compression inner side. So theta in that case we will consider negative. Theta in that case we will be considering negative, right? So this theta 1 here is basically negative minus theta 1. Similarly here, this moment is again producing compression in the inner fiber, and tension in the outermost fiber, okay? So again this will be theta 2 negative, right? Here in this, due to this moment, we can see that these moments, the compression will produce outside and tension will be inside. So that theta we will be considering positive, okay, right? So you can see that due to this moment, this side will be in compression and this side will be in tension, right? So that theta we will be considering positive. So this will be positive theta 1, this will be positive theta 2. So total theta will be theta 1 plus theta 2, right? You need to understand this thing, okay, because this thing we will be using in solving the calculating the collapse load, using collapse load in combined mechanism, okay? So this is how you decide the direction of the sign of the rotation, sign of the rotation basically at this plastic hinges, okay? So now, next step is to calculate collapse load in sway mechanism. Okay, this is very, very important. Okay, so basically in sway mechanism, what will happen? Let us suppose this is our frame. Okay. This is natural hinge, right? In sway mechanism, and one load is applied over here, 0.5 W, and here the vertical load is applied, W. Okay. So when sway will happen, this joint, the plastic hinge will form at this point, and at this point. We have already discussed that in sway mechanism, the plastic hinge will form at the top and the bottom of the column. Okay. So here you can see that the plastic hinge is forming at the top of the column. Okay. Here also the plastic hinge will form at the top of the column and bottom of the column. Okay. So in the sway, this joint will move perpendicular to this. Okay, we are neglecting the basically axial deformations, so this joint will move perpendicular to this. Okay, and similarly this joint will move perpendicular to this member. Okay. So this is basically our, what you can say that the plastic deformation during collapse. Okay, during collapse basically. Okay. This angle will be 90 degree, right? So this is the case of sway. Okay, this is our sway displacement during collapse. Okay, during collapse. Right? Now the important thing. Now, let us suppose this angle is beta. Okay, this angle is, let us suppose, alpha. Okay, right? So this angle is beta, this angle will also be beta. Alternate angles, this is parallel to this axis. Okay, if this angle is alpha, this angle will also be alpha. These two lines are parallel. Okay, and let us suppose this angle is theta, so this angle will also be theta. Alternate angles. Okay, now we will be using some geometry concept over here to find the relationship between these alpha, beta and theta. That is our whole purpose. Okay, so now you can see that okay, so at this point, what will be this displacement? Let us suppose this is C, this is C dash. What will be CC dash? CC dash will be equals to this distance, this is 6 meter. I can write 6 into beta. Okay, if beta is very, very small. Similarly, here the horizontal displacement will be this. Let us suppose this is delta dash. Okay, this delta dash will be, I can write this delta dash will be equals to what? This is B dash. BB dash is what? BB dash. BB dash I can write, this is 5 into alpha if alpha is very, very small. Okay, so the component of 5 alpha in this direction will be equal to this 6 beta. Okay, this in horizontal direction, this shear displacement should be equal, for because members are inextensible, right? So this delta dash should be equal to CC dash. Okay, actually rigid or member inextensible, you can say that member inextensible. Okay, so this is okay. So now what will be this delta dash? Delta dash I can write BB dash into cos some theta will into this. We need to calculate this value. Okay, this value will be equals to, let us suppose this is coming out perpendicular. This angle we know 4/3, tan inverse 4/3. So tan inverse 4/3 is basically 53.13. Okay, this angle is 53.13. Okay, this is delta dash and this is B dash. So this angle will be 36.87. This complete will be 90 now. Okay, so this angle will be 36.87. So I can write delta dash equal to BB dash into cos 36.87 degree. Okay, right? And BB dash, we know that BB dash is what? 5 alpha. Okay, so 6 into beta should be equals to 5 alpha into cos 36.87 degree, right? So if you calculate, if you find the relation between alpha and beta from here, it will come out to be 5 into cos 36.87. This is 6 into beta, this is 4 alpha. So alpha is equals to 6/4 beta. Okay, so this is nothing but 3/2. So alpha is equals to 3/2 beta. Okay, or you can say that beta is equals to 2 alpha by 3. right? So now this is okay. Next we have to find the relation between this theta and this alpha, or you can say that this theta or beta. Okay, so if you see this vertical displacement, this displacement, this will be equals to, again, this is delta dash, this angle is 36.87. we have already discussed about this, so we need to calculate this displacement. Okay, this displacement will be equals to, this is 5 alpha into sine 36.87. okay, and this will be equals to nothing but, this will be equals to this total distance is 12. This will be equals to 12 theta. Okay. Actually, this diagram I have shown in little a large view I have shown. Okay, but this displacement should be these are very small displacements. Okay, these are very small displacement. So you need to write 5 sine 36 into 12 theta. Okay, this actually, this BB dash will be very small. Okay, this BB dash will be very small. So this BC dash, B dash C dash is very close to BC. Okay, so this B dash C dash is basically, B dash C dash is basically equals to 12 meter only, right? So I can write 12 theta from here. So 5 into sine 36.87 is 3 divided by 12 equals to theta. So from here alpha is equals to 4 theta. So if alpha is equals to 4 theta, beta will be equals to 8 by 3 theta. Okay, so we have find the relationship between all the theta components. Okay, all the joint rotation and this plastic hinges, right? And this alpha, beta and theta are very small. Okay, so this is okay. So I'll write the relationship here. Alpha is equals to 4 theta and theta is equals to 8 by 3 beta. So now we will be using the principle of virtual work again. Principle of virtual work to calculate the collapse load in this frame mechanism. Okay, so principle of virtual work done states that the external work done will be equals to internal work done. External virtual work is equals to internal virtual work. So this internal virtual work is basically this theta is our basically the virtual displacement over here. This virtual displacement. Okay. So what will be the external work done? So external work done will be okay. External work done will be equals to 0.5 W. What is this delta dash? Delta dash we have already calculated. 5 into alpha. Alpha, in place of alpha I can write 4 theta. Okay, 4 theta into cos 36.87. Okay, now this in this problem there will be actual virtual work done due to this W load also. Okay, when the columns were perfectly vertical, in that case this load is not contributing to the external virtual work done in the sway mechanism. But here you can see that if you incline the column, this member will also rotate. You can see that this member BC is also rotating. Okay, so there will be some work done due to this W load also. Okay, so that will be equals to W into 8 theta. Okay, right? So this W is acting at a distance of 8, so this will be equals to 8 into theta. Okay, right? when the plastic collapse will happen, this position of W is also will also be shifted. Okay, don't get confused, right? When the plastic deformation will occur, this W will also shift to at some place. Okay, right? So this W into 8 theta will be equals to plastic hinges are forming at this B dash, this point, and this point. Okay, so I can write here MP into, here the direction of the rotation is like what you can say is clockwise. Here the direction of rotation is anti-clockwise. So both the theta will add. So this is alpha plus theta. Okay, if someone asks you what is the net rotation between these two members, that will be alpha plus theta, because both the thetas are in opposite direction. It is like this. If this is the angle between two members is 90, if this is rotating by beta, and if this is rotating by alpha, then the change in angle change in angle is basically alpha plus beta. Okay, so you can see that this is clockwise, this is anti-clockwise. Same thing happens here. Okay, plus MP into, at this point the work done will be again theta plus beta, right? And at this point the work done will be, internal virtual work done will be MP into beta. Okay, now we'll be putting the value of, now we'll be using this relation and putting the value of alpha and beta over here. So alpha is nothing but this is 4 theta, beta is nothing but this is 8 by 3 theta. This is 8 by 3 theta. Okay, so if you solve this thing, 5 plus 1 plus 8 divided by 3 plus 8 divided by 3, this is nothing but MP into 34 by 3 theta, and this external virtual work done will be 0.5 into 5 into 4 into cos 36.87 plus 8. This is equals to 16 W theta. This is 34, I think. 34. So the value will be 34 divided by 3 divided by 16. Okay. So this is equal to nothing but MP into 34 by 3 theta. Okay. So theta will cancel out each other. So if you calculate W from here, it will be 0.708 MP. Okay. So when you are considering sway mechanism, the collapse load W comes out to be what? 0.708 MP. Okay. Now what about the direction of the sign of the rotation of plastic hinges? Okay, that we will discuss. Now we will be discussing what will be the direction of the rotation of sign of the rotation of the plastic hinges, right? Because this thing is very, very important. Okay, so here this is our frame, okay, and this is deflecting like this. Here the direction of the rotation is clockwise. Okay, this is alpha. This is alpha, or you can say that 4 theta. This is anti-clockwise, this is theta. This is again anti-clockwise theta. This is clockwise, this is 8 by 3 theta. This is anti-clockwise, this is clockwise, this is 8 by 3 theta. Okay. What we are doing here is we are checking the sign of the rotation, what sign we need to, whether this theta is positive or negative. That thing we are about to discuss. Okay. So as I have already told you, the direction of the plastic moment for this portion, this theta is in which direction? Anti-clockwise direction. So the moment will be in clockwise direction NP. If for this member, for this AB member, the rotation is in clockwise direction, so moment will be in anti-clockwise direction. Okay. Now, this moment is basically producing compression outside. So this theta will be positive, right? Again, and this theta, this moment is again producing compression outside. So this will also be positive, right? Similarly, at this point, this theta is what? Clockwise, right? Anti-clockwise. So to oppose, there will be some clockwise moment. Okay, and here this is what? This is anti-clockwise. So moment will be anti-clockwise, right? So what is the situation? Situation is like this. Here the moment is acting like this, and here and this moment is acting on this column, and this moment is acting on this beam, right? So this is producing compression inside and tension outside. This is producing compression inside, tension outside. So this will be negative, this is negative, and again this will be negative. What about this? Due to this is clockwise, the moment will be anti-clockwise. So anti-clockwise moment will produce compression outside, tension inside. So this is positive theta. Okay, so this is nothing but this is positive, right? So in this way, we decide the direction of the sign of the rotation of this plastic hinge joint. Okay. Right. Now, this thing is done. So now let us combine mechanism 1 and mechanism 2. Combining mechanism 1 and 2. Okay. Now we'll see why we understood how to calculate the sign of this rotation. Why to consider the sign of the rotation? Because in the previous lectures we didn't consider these things, but here we need to consider these things. Okay, because our problem will become much easy, right? So now, what is the purpose of combining mechanism? That thing we have already discussed. The purpose of combining the mechanism is to minimize the internal work. Minimize the internal work. And how the internal work is minimized? Internal work is minimized how? By cancellation of hinges. Cancellation of hinges. So in the combined mechanism, our criteria should be to maximize the external work and minimize the internal work, right? To maximize the internal work, to maximize the external work and minimize the internal work. That should be our criteria in the combined mechanism. Okay. So basically, here what we will do, we will be at the B point, we will be cancelling the formation of hinges. Okay. We combine two mechanisms in such a way that the plastic hinge won't form at this B point. That is our criteria, because ultimately we need to find the critical load. Okay, critical load we'll find when the internal work done will be minimum. Okay, because our external work done is equals to internal work done. Okay, so if internal work done is minimum, this is internal work done and this is external work done. So W will be minimum when W will be maximum when internal work done will be minimum. Okay, right? So this is okay. So we will be combining mechanism 1 and 2 in this way that the plastic hinge won't form at this B point, right? So this is okay. Now let us check the direction which we have already discussed in beam mechanism. Sign of the directions, sign of the rotation basically. Here, this is theta 1, this is theta 1 by 2, this is theta 1 by 2, this is theta 1 theta 1, this is theta 1 by 2, right? And here also, we already discussed this thing. This theta 1 was negative, this theta is negative, this one positive, this one positive, right? So now if you see, if in this figure, if we see this, after sway, initially the angle between the, let us suppose angle between these two members is, let us suppose x degree, okay? And when the sway occurs, the change in angle between these two members is basically what? Alpha plus theta, or you can say that 4 theta plus theta, which is equals to 5 theta. Okay, there should be no doubt in this. Okay, if after sway the change in angle between these two members, let us suppose this is y degree, so x minus y is equals to 5 theta. Okay, and basically we are considered about this 5 theta only, because in internal work done we basically consider this change in angle. Okay, so this is okay. Now in the B mechanism, what is happening? This is our frame. Initially the angle between the members is x. Now if it is, let us suppose z, so the change is basically is equals to theta 1. Okay, so that if the plastic hinge should not form at this point, then the angle between, the change in angle should be equals to 0. Angle should not change. Okay, angle should not change, right? So I can write theta 1 plus, or you can say that here the theta is basically negative, so minus theta 1 plus 5 theta is equals to 0. Okay, so from here theta 1 is equals to 5 theta. So this is the relation we used. Okay, so if theta 1 becomes equals to 5 theta, then the plastic hinge the plastic hinge won't form at this B point if we combine mechanism 1 and mechanism 2. Okay, that is the purpose basically. So this is okay. Now, right. So this is okay. Okay. So theta 1 should be equals to 5 theta. Okay, because if theta 1 is equals to 5 theta, what will happen? Let us see. If theta is equals to 5 theta, right? Okay, this theta is changing rotation in this BC, and this theta 1 is changing rotation in this BC member only. Okay, so if you combine both these two things, the deformation, if you see the sway deformation, how the sway deformation will look like. So if you combine these two things, okay, so what happened is that at this point, this theta plus this theta 1, this is in anti-clockwise, this is in clockwise direction. Okay, so net rotation will be in clockwise direction. Okay, so if you draw the plastic hinge at this location, if you show the rotation of the members at the plastic hinge, it will be like this. If this is B point, this is the initial of our member, so this will be alpha, or you can say that 4 theta. And similarly, if you combine these two things, these two rotation in these two members, it will be 4 theta, and that is in clockwise direction. So this is also equals to 4 theta. Now you can see that this is rotating by 4 theta, this is also rotating by 4 theta. So there won't be no net change. Net change will be equals to 0. Okay, so plastic hinge won't form over here. Okay, understood? Now, one plastic hinge will form at this under this point load. Okay, so I'm showing this. This is that plastic hinge. Okay. And again, it will deform like this. During collapse, it will deform like this. Okay. We cannot cancel all the hinges because we need to form some mechanism should be there. Okay. Some mechanism should be there, right? This is natural hinge. So now let us discuss about this point. What will be the net rotation after combining these two mechanisms? Okay. So at this point, in beam, the rotation is the rotation is minus theta. Here also the rotation is minus theta 1 by 2. Okay, so both the rotation will add theta 1 by 2 plus theta 1 by 2 minus these, both are of negative sign, right? And theta 1 we already calculated. Theta 1 is nothing but this is equals to what? 5 theta. Okay, so this is minus theta minus 5 theta by 2. So this will be equals to 3.5. Okay, because if you are keeping this theta 1 is equals to 5 theta, then this theta should be equals to 2.5 theta. This relation we have already calculated. This relation won't change. And if you are increasing this theta, your collapse loading beam mechanism also won't change. Okay, you can check. Okay, collapse load in beam mechanism won't change. Okay, if you put this theta 1 is equals to 5 theta, right? So this is okay. So at this point, the rotation will be 3.5 theta. Similarly, at this point, in this portion, this column, there is no rotation of this member, this particular member, this column. Here, there is a rotation of minus 8 by 3. So again, this will be 8 by 3 theta. I hope the concept are clearing. You are able to understand the concept, okay? Because it is little bit tough, right? Here also, again, the direction of the rotation will be 8 by 3 theta, and this is basically positive. Here, this is this will be 2.5 theta, and this will be equals to 5 theta. Okay, at this hinge, what will happen? Theta 1 we have put theta 1 is equals to 5 theta, so this will be 2.5 theta. Okay, I'm telling you that collapse load in beam won't change if you increase theta 1 by 5 theta. If you multiply 5 theta, if you provide this displacement equal to 5 theta, then this collapse load in the beam won't change. Okay, collapse load won't change. Okay, you can check that thing. It is very simple. Theta will cancel out each other. Okay, nothing will happen. This W is equal to 3 by 4 MP will come. Okay, so I'm not showing that thing. So this is the final diagram. Combined mechanism. Okay, displacement, or you can say that deformations during collapse. During collapse, this will be the frame will look like this. No plastic hinge. Okay, and this here, in this case, the virtual displacement over here is basically 5 theta. Okay, it's in our hand basically. Okay, because we need to find the critical case. Okay, so this is okay. So plastic hinge is not forming, so only the plastic hinges are forming at this point, at this point, this point, and this point. Now we will be using again the concept of concept of principal virtual work. And what is principal virtual work states? It states that the external virtual work done is equals to internal virtual work done. Okay, so again, external virtual work is equals to internal virtual work, right? So I hope this thing is clear to you. Okay, so when the external virtual work done is equals to internal virtual work done, okay, here the load acting is 0.5 W here at the hinge location the load is W, right? This distance will be 8. And again, our horizontal component will be this one, and that we have already calculated. Okay, this was coming out to be 0.5W into what? Into 4 theta into 5 into cos 36.87. Okay, I'm not going to discuss this thing again, right? Due to this W load will be W into this displacement, and this displacement will be equal to this thing. You can make mistake over here. This should be equals to 8 into 3.5 theta into W. Don't write 8 into theta. Total rotation now in combined mechanism here is 3.5 theta. Why? We have already discussed, right? So 8 into 3.5 theta into W. Okay, this should be equals to our internal virtual work. Internal virtual work will be taking place at this point, and this point at the location of the plastic hinges, right? So at here, the moment is MP. The net rotation is basically 5 theta. This is 5 theta. 5 theta plus 2.5 theta. Okay. Plus. At this point, it is nothing but MP into 3.5 theta plus 8 by 3 theta, right? Plus MP into 8 by 3 theta. Okay, guys. So if you calculate the value from here, this will be 5 plus 2.5 plus 3.5 plus 8 by 3 plus 8 divided by 3. So this is coming out to be 49 by 3 theta into MP, and this external work done will be equals to 0.5 into 4 into 5 into cos 36.87 plus 8 into 3.5, and this is coming out to be 36 W into theta. Theta will cancel out each other, right? W from here will be 49 over 36 into 3 MP. So what will be the value? 49 divided by 36 divided by 3. So the value comes out to be W is equals to 0.453 MP. This is the collapse load in combined mechanism. Okay, so this is our collapse load. Combined the value comes out to be 0.453 MP. Now, out of these three collapse load value, this is our critical case. Okay, so we need to design our frame according to this load. Okay, so this is the problem. Little different problem here because here there is inclination of column. Okay, I hope this problem is clear to you. These are some very good concepts over here, how to check the sign of the rotation, okay? Because it is easy to understand, okay? In combined mechanism, we simply combine those rotations, okay? And we'll see how the members are rotating, basically, okay? Okay, guys? So, if you have any doubt in this problem, you can write in the comment section, okay? How this rotation is, how we consider the sign of this rotation. This is very important thing over here, okay? This thing we'll discuss again in some other problem. Again, we'll discuss all those things. Okay. So thank you very much. We'll meet in the next lecture.